Hello, and welcome to An Unpolished Earthling, a channel where we discuss pathways to a healthy future. Today we'll be looking at climate change models. We'll start briefly at looking at the latest IPCC report, which, as we can see, says we have unequivocally caused global warming. And we're going to look at a few other science communicators to see their perspectives on this, and we'll see that their perspectives range a fair bit. So to help us understand why everyone is not so certain about exactly what will happen in the future, we're going to build our own climate change model to see what goes into making one and what kind of estimates and assumptions that we make along the way, how those will affect the accuracy of the model at the end. This will be a fairly long video, but we're going to learn a lot about how climate change works and what we can do about it, and hopefully understand better why some people think that we are already totally screwed and have no chance of success, whilst others are not so concerned and think we have a fair bit more time to deal with the problem. So now let's have a quick look at what some other people have to say about this issue.
The land-ocean increase was 1.14 degrees C from pre-industrial, but the land increase is 1.47 degrees C, nearly 1.5 degrees C. And please note that practically all the increase has come from the northern hemisphere. So here are two records from GISS of the northern hemisphere temperature increase, because emergency correction of climate disruption, the emergency which the IPCC has done very well on, particularly the chair, Dr. Lee, is that emissions had to be put in decline immediately. They used the word immediately over and over, and they've used the word immediately here. This is in all our best interest. This is for the survival of all of us, all of humanity, everywhere, all life, everywhere. Emissions have to be put into immediate and rapid decline. It's simply a question of converting from fossil fuel energy to clean, renewable, which means everlasting energy.
Here, off from school, but with permission to say.
Hi, yeah.
To start first.
I'm the youth representative for XR, and I wanted to talk about where the youth are coming from with this crisis, and I wanted to start by talking about my climate reality, which is quite a harsh reality, which is the fact that my family, my brother, my friends are going to struggle from this. Our dreams are being taken away from us because of this. We're going to starve, and we're going to go hungry because of this crisis. And that is something that scares me. And that is something that, honestly terrifies me. Because when I'm older, I want to be able to focus on my dreams, which is to become a musician. And at the current rate of time, that is not going to happen, because I'm going to be seeing war, famine, and mass natural disasters instead. And this is something the youth across the globe are seeing and feeling. And this is why the youth are acting. And this is why we're in the streets begging for a future. But a big issue we are facing is the lack of youth understanding in so many of our youth today. Still, so many of our youth don't understand the crisis we're facing, and this is something that isn't okay, because it means we aren't going to be able to move forward, because we are the future, and without full understanding of what we're facing, full transparent and clear understanding of both the science and the social issues we're going to face because of what we're dealing with, we're not going to be able to reach the targets we need to reach to create a sustainable future.
I probably need not point out that I erred previously with respect to human extinction, as you will undoubtedly indicate in your forthcoming article. Yeah, undoubtedly. I quoted from the scientifically conservative 2012 issue of Annual Review of Earth and Planetary Sciences, and concluding that the loss of Arctic sea ice will lead to loss of habitat and therefore extinction of our species. The paper was titled The Future of Arctic Sea Ice, and I include a link to it. It projected an ice-free Arctic Ocean in 2016, plus or minus 3 years. I believe my prediction referred to 2018 as the final year for Homo sapiens. And since then, of course, we've had papers come out in 2020 in the peer-reviewed journal Science by Mark C. Urban, indicating that loss of Arctic sea ice will drive our extinction. The article is called Life Without Ice, and it indicates that it will lead to loss of habitat, the most rapid change in planetary history because the rapidity of change will cause our extinction. Now, he says this is about 3 decades away. Meanwhile, Professors Jennifer McKinnon at University of California, San Diego in the Scripps Institute, and also Professor James Anderson at Harvard University have indicated that this is the year we're going to have an ice-free Arctic Ocean with full effects to be realized next year. In other words, what that means is the equivalent of 1 trillion tons of carbon dioxide released into the atmosphere all at once. Add on the fact that we are breaking out of a triple dip La Nina and headed into a El Nino Southern Oscillation period, which is further going to warm the planet. You add that to the loss of Arctic ice, almost certainly including this year. We'll know in early April for sure. And it looks like, in fact, we're doomed. And this is not something that I want to happen. I keep saying this over and over again. People accuse me every day of wanting this good to go extinct so that I can be proven right. Trust me, my ego is not that big. After all, at the edge of extinction, only love remains.
Question, I say, when would we hit them in terms of time?
Exactly.
Yeah, I always get this question, and it's impossible to answer because apart from the ones that have already happened, it depends on emission scenarios again. So we might never see 3 degrees, or we might see 3 degrees in, I don't know, 2045 if we're really stupid and unlucky. So to get to the worst case scenarios of close to 6 degrees by 2100, you have to scroll through the through the degrees quite quickly during this century, which means very, very high emissions. And if you I think it's important to remember that if you look at and the Met Office has done some work on this quite recently, that temperatures level off very quickly after you stabilize concentration. So if you get to net zero, you don't then, well, feedbacks aside, you don't then see a world where you've got temperatures continuing to increase. Actually, if we get to net zero and we are generally not, we're not pushing the Keeling curve up any higher, and we're actually at level concentrations, the warming would stop almost immediately, like literally within a matter of years. So that suggests that we can solve this problem. And in some ways, I think people often look at the feedbacks and obsess about the feedbacks, and it's like, oh, it's beyond our control. It's a psychological crux to imagine that we can't do anything. Actually, we can, and the feedbacks aren't that significant on the decadal timescales. It takes quite a long time to melt the permafrost. It certainly takes a very long time to melt the ice sheets. It takes centuries. So this is why I don't see sea level rise as an extinction, as a kill mechanism. And there isn't necessarily even that much carbon, even in the Arctic permafrost, to drive concentrations. It might be another 30, 40, 50 parts per million. I'm not sure what the exact figure is. I don't think anyone knows, but it's not like another 1,000.
And then we celebrated. We were like, yeah, we're the first to have a target, job done, right? But all the actual policies that that govern what happens in this country haven't been changed to allow us to meet that. Famously, we've approved a new coal mine, and there are hundreds of new oil and gas licenses in the North Sea. But beyond that, we're planning to expand airports. We're still building new roads. We're still building new houses to really bad standards that are going to have to be immediately retrofitted if we're going to decarbonize. So, what's the point of having a 2050 target if all your actual policies are taking you in the wrong direction? It's not like the policies are taking us in the right direction but too slow. They're taking us in the wrong direction. New oil licenses is the wrong direction. New roads and airport expansion, it's the wrong direction. So this is hugely problematic. And there was this really stark sentence just buried in a paragraph in the middle of the report. It said, without a strengthening of policies, global warming of 3.2 degrees is projected by 2100. As things stand, we can expect to see global warming of 3.2 degrees by 2100. Now, there's two very key things to think about here. One is that we have no clue what a 3.2 degree world would be like, but there is absolutely no evidence, there is no suggestion at all that organized human society could exist in a 3 degree world. You know, our societies are so complex and interdependent that there's you know, lots of very, very serious people just don't see how something so complex could survive such rapid changes. So, and you know, we're talking about the risk of collapse of civilization, the end of organized human society by 2100. And this report is saying that that could happen. Well, it's not saying that we could get collapse, but it's saying we could get 3 degrees. And at 3 degrees, a lot of people say we'll get collapse. The other thing that's really important to always, always, always remember when we're talking about 3 degrees by 2100 is that people already born today should, all other things being equal, should still be alive in 2100. And like, we're not talking about theoretical people. We're talking about my nephews and nieces. They should be alive to. It's just, yeah, it's just extraordinary that after everything.
So just as they're not in these things saying what should be done, i.e. find a way to force the action to happen against perhaps the will of the finance sector to say we'd quite like to still make money out of this, is also true, isn't it, that it's not telling anyone in simple language what things really mean, right? Because if you bury in the middle of a report something that says, you know, basically it's going to hit 3.2 degrees, and let's remember that we just said it could have 0.8 baked in as like a masking effect, so that already takes you over to 4. With all that in mind, the question does come, doesn't it? Should this report actually include the word collapse?
I think the reason it doesn't is because they could never get every nation to include that. Personally, yeah, I think it should. You know,
if it was being honest.
Yeah,
I mean.
Well, that's it. If it was being honest.
In the last 3 decades, these pollineas have become about 5 times more prevalent on the East Siberian Arctic shelf, allowing methane releases all year round. And just to really help the situation, the shelf sits on an active tectonic plate, so earthquakes and tremors are a feature. According to Shakova's team, any destabilisation of these hydrates could result in a massive release of methane, but until relatively recently, the conventional wisdom was that this effect was negligible on a decadal or century timeline. And so the continental shelf of the Arctic Ocean hasn't as yet been considered as a source of methane into the atmosphere. And that's had big consequences for the predictive models known as representative concentration pathways, or RCPs, produced by the Intergovernmental Panel on Climate Change, or IPCC. Because it hasn't been possible for the scientists compiling these reports to reach consensus on the overall additional effect of Arctic methane on our planet's warming, they've so far simply elected to leave methane out of the predictive models more or less completely.
Alright, so now that we can see that some of the best models that we have are still not giving us very specific results, and there's still a lot of confusion amongst experts of what we expect to happen in the near future, we're going to build our own climate model so we can try to understand a little bit better about why this is the case. Now, to start with, let's imagine a very, very, very simple climate model where we're looking at when we expect the seasons to be and try to understand why it's summer in one place and winter in another. Well, if we imagine that the Earth is tilted and it's orbiting around the sun, we'll have winter in some places where we have summer in other places. And this model gives us a pretty good understanding of when we expect, or how we expect seasons to change and why they're changing. At the same time, before we understood that the sun was in the center of our solar system, we had a model where the sun was on the outside. And if the Earth was in the middle and tilted, that model, which is not really accurate to reality, would still have given us a good idea of why the seasons are changing and when they will change and how they relate to one another. And so as long as the model is built to reflect the data that's put into it, it can be useful in talking about that data. But if you were to say, where would we expect Mars or Venus to be in relation to the Earth and the Sun, our model that had the Earth in the center would not work for that. And so the more complicated our model gets, such as if we put the Sun in the center and added all the planets where they should be, the more answers we can get out of it and the more we can learn. Now with the climate change model, we're looking at an infinitely complex system. So to get a climate change model that is going to be very accurate to tell you how much rainfall you're going to receive in a part of Europe exactly 50 years from now and what the temperature will be, you would need an infinite amount of data to get an accurate answer out of it. And we don't have that capacity. So that's why climate change models use a lot of approximations and estimates, and because of that, they're never going to give us a true prediction of what the future will be like. Nevertheless, as we look at how we make those assumptions and estimates, it'll give us a better idea of, are we skewing things to a higher temperature or to a lower temperature? In other words, are we making a conservative estimate of how changes will happen, or are we making a hyperbolic or exaggerated estimate of how things are changing? And as we build our climate model today, we'll get a much better understanding of all of the facets that we are either including or not including and how that'll affect the end of the model. Although we're going to go over that in the conclusion of our video today, because building the model itself is going to take a long time. Hopefully not for the video, but yeah, there's a few steps involved here. Now, let's begin. We will notice that there are two main sources of energy for the Earth, the Sun and the Earth itself. And if we look at geothermal energy, we notice that the core of the Earth is very, very hot. And as we get towards the edge of, well, the crust of the Earth, there's a lot less energy. So if we go back here for a moment, so at the base of the crust, 1,000 degrees, and at the center, 5,000 degrees. But near the crust of the Earth, it changes by 25 degrees Celsius per kilometer. And at the very outer edge of the Earth, we still have some places like Antarctica that are frozen solid. So therefore, the geothermal heating of the Earth is not the main driver of what we're experiencing at the surface. And actually, if we look briefly at how we calculate global average temperature, and that's what these reports are talking about is changing, we are looking at measurements from the air above the land and the ocean surface. Which is to say, we're not looking at the whole planet, we're not looking even at the entirety of the ocean when we're calculating global average temperature changes. So in regards to our model for climate change, we are just not going to include geothermal energy as part of our climate change model. So there is one consideration that is going to affect its predictions of reality right away, because if the geothermal energy changes over the long run, which it does over millions and millions of years, then it would change our climate model. And if our climate model doesn't include that, then our climate model will be wrong if we look at what happens 10 million years from today based on our climate model. But our climate model is not going to be asked, well, we're not going to ask it what happens in 100 million years. We're going to be asking it what happens in a few decades from now, or perhaps in 100 years from now. And on that time scale, the geothermal energy is not significant, and that's why we are going to ignore it. Next, the solar energy, when it arrives at the surface of our planet, is hitting every square meter with 1,360 watts. Now, a watt is 1 joule per second. Now, when the sunlight hits the Earth, it is hitting an oblate spheroid, which is to say that the Earth is roughly a ball, roughly a sphere. And if the sun is over here, the part of the Earth that is flattest in regards to the incoming light, so the most directly facing, is going to get more intense light than the parts that are further towards the poles, as we see here. Now, if we put this into practice, we end up with a chart like this, which shows us the amount of energy hitting the surface of the Earth based on the curvature of the Earth. However, when we look at the energy that actually hits the surface of the Earth, the map's more like this. So vaguely we see more energy near the equator. and less energy towards the poles. That's consistent. However, we see anomalies here, 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 and here, and that's because this is desert and desert and desert, whereas in these areas there is the Amazon rainforest and the Central African rainforest here. So there is a lot of cloud cover, which is reflecting light away, or blocking light from hitting the surface of the Earth. So our expectation of how the energy will hit the planet is different than how it does hit the planet, which means in our climate model system we're going to have to include some cloud cover, and we're also going to have to include the curvature of the Earth. But more than that, there's going to be albedo. And if we look briefly here, we can see that different surfaces of the Earth reflect different amounts of light. And so open ocean absorbs almost all of the sunlight that hits it, 94%, and reflects about 6%. Asphalt, like on roads in the city, absorb 96% or reflect only 4%. And a desert reflects 40%. And fresh snow reflects 80%, and shiny aluminium is reflecting about 85%. So if we look at the albedo of the planet, we see that near the poles there's a lot more ice, so the albedo is a lot higher, and near the equator there's a lot more open ocean, so the albedo is lower. And unfortunately for us, if we look at the way that sunlight is hitting the Earth, that means that where we're reflecting the most energy is actually where we're receiving the least energy. And where we're absorbing the most energy is where we're and where we're receiving the most energy is where we're also absorbing the most energy. So for our climate change model, we're going to begin with thinking about the energy coming into the planet as the sunlight in watts per meter squared. We're going to break up the planet into a grid like this, and we're going to look at the albedo of each part of the land based on where it is on the grid, and the angle of light coming into it to calculate the total amount of sunlight that we are receiving each year. And if we do that, we get a grid something like this, which will tell us where the albedo is in different places and the average total albedo for that area. Now, unfortunately, when I was making this, I forgot that my program saves automatically, so I set up the first albedo for how the world would look like as it was in 1750. And then set up another grid for how the world would look like if it reached 18.5 degrees global average temperature, so with a lot more increase, using the IPCC reports of how they expect ice to melt, sea level to rise, and changes in forest cover due to droughts, and in some places increased precipitation, which may increase vegetation cover in those places. So this is a grid of what happens when we are in a hot world, and this is the global average albedo per latitude for that grid. And this is the global average albedo per latitude for a grid as it was in 1750. And we can see one of the huge changes is up at the North Pole. We used to have a lot of ice, and now, well, not now, but at 18.5 degrees global average, we would have no ice at the North Pole, maybe tiny little patches over here. And then in the South Pole, we see that there is less of degree of change, and that's based on the majority of climate change models that we're looking at. It seems that the South Pole is slightly buffered from the changes in temperature, and part of that is because Antarctica is a continent, whereas at the North Pole, there's the sea ice is floating. And so the circulation of warming water underneath the North Pole will melt that ice much faster than the ice in the South Pole. And that's why we have this result here. Now, if we calculate based on the average angle of the sunlight hitting this average albedo, we can get the average solar input per meter squared in kilowatt hours. So this is for 1 hour of direct sunlight over this area. And if we add up all of the energy we get by doing it this way, we get this global average input per meter squared in kilowatt hours for our warmer planet, and this amount for our colder planet. And we can see that just by changing the albedo, we get more energy when the planet's warmer. And this is a feedback loop. Now, we're making a model and we're going to run through a whole lot of math when we're doing it. So if we have to change the albedo in this grid as we're going along to get a more accurate number, it's going to take a long while. And instead of that, we're going to calculate a global average albedo, which are these numbers for our cold world and our warm world. And if we take the global average angle of deflection, or angle of incidence for the light, and we multiply it by the global average albedo, we get these numbers for our warmer world and our colder world. And we can see that they're not the same. And this is an example of how whenever we basically pixelize data, so in other words, the world should have an infinite number of different parts of land with different parts of albedo because there's so much area of the world, so this should be much more detailed. And as we summarize it and make these squares represent a bigger portion of the Earth, the data gets less accurate. And even though this does represent an average of the whole world's albedo, it is, when we include the global average deflection, what we're doing is we're changing the importance of the north and south poles compared to the equator. So in the global average, the North Pole albedo is being affected by the same amount of energy as the equator albedo, whereas in the longer form math, it doesn't work that way, and we end up with quite a different number. So just to get an idea of the difference in scale, we are off by about 4% in the warmer world, and we're off by about 10% in the colder world. So we're basically going to know that we're taking our model with a grain of salt immediately by using more simple math. Now, if we take our albedo changes and we take our temperature changes, we can make a chart with how we expect the global albedo to be for whatever global average temperature we have. And we can also see how the solar input per meter squared is changing at the same time. So now we've got our albedo chart, which tracks with temperature, and that's part of the feedback loop we're going to include in our climate model. Now, the next step is to add in greenhouse gases. So we're getting a certain amount of solar input per year, and that's being affected by the global albedo, but how much of that energy is being trapped and kept as heat? So let's have a brief look at a clip from a video by Sabine Hassenfelder to look at how the greenhouse gas effect works.
I've tried to figure out why I misunderstood this for so long, and I think what threw me off is all those arrows for infrared light that go right through the atmosphere. I think it'd be better to draw it like this. The incoming radiation from the sun goes through the atmosphere and hits the surface. It's converted into infrared radiation, and that heats the atmosphere from below. Somewhere up here, the infrared light escapes for good. If the concentration of carbon dioxide goes up, then the infrared light escapes from somewhat further up, where the atmosphere is a little colder. So now the total emitted energy is smaller and the system is out of balance. The Earth then has to heat from below until the emission comes into balance again. And the effective altitude of emission can be slightly different for each part of the frequency spectrum. I believe that those pictures originate from illustrations in climate physics books where the arrows don't depict the way that the radiation actually goes, but just the total amount of energy that flows through those channels. That's to say, this illustration is all well and fine so long as you don't think this means that the infrared light actually goes through the atmosphere.
All right, now let's briefly look at greenhouse gases, carbon dioxide equivalents, and carbon, and what all these things mean. Greenhouse gases are gases that affect the temperature of the planet. Carbon dioxide is one of those specific gases which we usually focus on because of the sheer quantity of it that we put into the atmosphere. CO2 equivalent includes most of the other gases which are also included in the greenhouse gas effect, except for water vapor. And carbon is an element which is found within many different greenhouse gases, such as in CO2, there is 1 atom of carbon for every 2 atoms of oxygen. Now, there are a bunch of different greenhouse gases. We're excluding water vapor in this chart. I wish they didn't, but we'll get back to water vapor later. Here, what we're talking about is that different greenhouse gases have different effects, and methane is 25 times more powerful of greenhouse gas than carbon dioxide for every kilogram. But the effect changes over time. And so this scale shows us the effect of greenhouse gases over a 100-year period. The thing we should take into consideration is that methane degrades significantly over a 100-year period. So if we look at, say, the 20-year effect of methane, it's actually a lot higher. And we can see that instead of the 25 times over 100 years, it's 86 times more powerful over 20 years. And since we're looking at climate change happening right now, it might be worthwhile considering a higher number for some of these things in the chart, or at least acknowledging that if we were to do calculations of how we expect change to happen, and we don't consider this, then our models will be wrong. So when we're building a model, acknowledging that it can be inaccurate depending on the time frame we consider when looking at the different effects of greenhouse gases, we're now going to look briefly at trends in atmospheric concentration. And we can see that carbon dioxide is increasing dramatically from around 280 parts per million to 407 parts per million in 2018. And obviously higher now, and it seems that the rate of increase is also increasing. If we look at methane, a similar thing is going on, and if we look at nitrous oxide, a similar thing is going on. Although we'll see that nitrous oxide is measured in parts per billion, and so is methane. And that's why it's simply the sheer volume and scale of the carbon dioxide, which is why we primarily focus on it. And to get a better understanding of CO2 equivalent, back in 2021, we were at about 415 parts per million of CO2 alone, but including the other gases except for water vapor, we were at 508 parts per million. What does this mean in terms of changing the temperature of the planet? Well, understanding that the temperature will change based on quite a few factors, not just CO2 concentration, but looking at just that portion of the effect, if we change the CO2 concentration alone to 550 parts per million, the IPCC expects that we will reach around 3 degrees Celsius of increased temperature. And what does that mean? Well, back in 1750, we were at about 280 parts per million, and the temperature was around 13.5 degrees Celsius. So if we take a quick look at our chart, we want to set up a chart that tells us what the temperature will be based on the amount of pollution if solar input remains constant. So in other words, if we don't change the albedo or have feedbacks like that. So we have this here, but you'll notice right away that the amount of pollution that I'm including is much, much higher than 280 parts per million for the 1750 temperature, and also much, much higher for the 16.5 degree expectation. And the reason for this is that I am including water vapor in our chart because water vapor is a major greenhouse gas. And so in terms of the total greenhouse potential, or in other words, how much of the energy we're receiving are we keeping, we have to include water vapor. But what number do we choose? Now here, I'm not choosing a very accurate number. I'm using 75% of the CO2 in 75% of the greenhouse gas effect in 1750 being water vapor and 25 being CO2 to give us 1,120 parts per million CO2 equivalent, including water vapor. Now, is this accurate or not? It's not, and let's have a quick look at why. The challenge is understanding how much of the effect of the greenhouse gas is water vapor, and we have very wide-ranging numbers. So here it says water vapor accounts for 97% of the greenhouse warming of the planet. Here it says it's about 60%, and if we look in a little bit more detail, we see it ranges at least from 36% to 72%. And the idea is that if you're in a desert, there's much less water vapor in the atmosphere above you. And so the effect of the greenhouse gas in that area has much less to do with the water vapor content. However, in a rainforest, there is much more water vapor in the atmosphere above that area, and so the water vapor will have a more significant effect in terms of the greenhouse gases. But for our model, we're looking at a global average, so we need to take one number that we're applying to our imaginary square meter of the Earth, that is our global average square meter. And for that, I'm choosing 75%, and you can see it's a little bit high, but we'll see why in a moment. Now, the reason I did that is that if we keep the specific amount of water vapor from 1750 the same as it is today, which again is not totally accurate, then we're only at about 62% of the effective greenhouse gases being water vapor for today, which does fit within the margin of what we saw on Wikipedia. Although this means our model might be a little bit off in the 1750s, but I don't have good data for that, and we're just going to run with this estimate and acknowledge that we're making an estimate yet again. Now, if we run through this chart, we need a way of transforming this amount of pollution into this amount of temperature. Now, to get this temperature, the idea we're using is that of the energy coming in, we're capturing a portion of it and transforming that into heat. So we need to turn our amount of pollution into a fraction. And to do that, we need a denominator, and we're going to invent one out of nowhere. And we're going to presume that there is a sort of saturation level of greenhouse gases, and so at a certain point we would capture 100% of the energy, and if those gases were, if the pollution was half that amount, we would capture half of the energy. Now, to pick this number, we can pick any number we want. We could say it's 10,000 or even just 5. But we also then need to transform the result into degrees. So once we have an amount of energy, we're going to say how many kilowatts of that energy is the equivalent of 1 degree Celsius that we're capturing. And just to show you what happens with the math, if we make this number bigger, this number gets smaller. And if we make this number bigger, this number also gets smaller. Now, there are many different pairs of numbers we could use. These 60 and 3040 are just arbitrarily the ones that gave me a nice fit. But we can see that if we chose 80 and 5000, it does not give us the temperature we want out of it. So this is how we are scaling our model to the data that we received by saying we expect this amount of pollution to give us this target based on the IPCC reports, and we know that this amount of pollution gives us this temperature based on what we observed back in 1750. So now we have a model that works pretty well to give us different temperatures based on different amounts of pollution. We can see it's not exactly perfect, but it fits quite well. So at 6 we're a little bit low, and at 30 we're a little bit high. But nevertheless, we now have a model that will give us our target temperature based on a certain amount of solar input and the amount of pollution in the atmosphere. So we can put this back into our climate model, and we can take that math and put it in over here. Now, all of this looks probably like a little bit much, so let's discuss what we're looking at. This here in the middle is the chart of the output of our model. So we can see that in 1750, if we had 280 parts per million with an albedo of what we expected it to be back then, there would be zero forcing, the idea of there would be a stable climate and we wouldn't be getting warmer or colder. The target temperature would be 13.5 degrees, and we were at 13.5 degrees. However, we were also increasing the global pollution by 0.1 parts per million per year. So by the time we got to 1880, we were at 287 parts per million with a slightly changed albedo because we had built more stuff. That meant that the solar forcing has increased. Don't get hung up on the specific number. We're just looking at, is it getting bigger or smaller? Is it negative or positive? And we see that our target temperature had increased to 13.58, so not a huge change. And our actual temperature had gone up only 0.03 of a degree Celsius, barely noticeably. And the amount of pollution we were putting in the atmosphere then had still not increased very much compared to how it was in 1750. In 2020, we were at about 507 parts per million, and our global albedo had changed because the temperature had gone up and melted some ice. The amount of forcing had gone up, and our target temperature was 16.35 degrees, which is not quite 16.5, but we're getting pretty close. Our actual temperature was 14.9 degrees, and instead of increasing the amount of pollution we're making by 0.1 parts per million, we were increasing by 2.8 parts per million, which is a dramatic increase in the amount that we're putting into the air every year. Now over here is the math that's actually happening in our model. And we can start at the top, and we see that we have built tiles with built albedo, world tiles with global albedo. So here we're saying, based on our albedo chart, what we expect the world to look like, but we have changed some of the surface of the Earth. And so the surface of the Earth in the scale of our model is 290 tiles out of a total of 1,000 tiles, with the rest being ocean. So we can only build on so much area, and in our model now, we've covered most of the land surface, which is a little bit of an exaggeration, but humans have changed more than half of the land surface. So we know this number should be at least around 160 at the absolute minimum, but probably not as high as 211. And where do we get this number from? So here's a fun part of the model where we look at what human beings are actually doing on the planet in terms of our cities, farms, factories, waste management, power production, etc. This is a huge oversimplification of what happens in the world. I haven't included a box for every type of industry that we have or every way that we affect the planet, but this does give us an idea of how, as we change what we're doing on the planet, we can change the amount of pollution we're producing. For example, if we build a new coal power plant, we see that we increase pollution. We can also see that if we change a monocrop farm that relies heavily on industrial chemicals and pesticides and isn't really good for the environment and requires a lot of fossil fuels, if we reduce one of those and use mixed species horticulture, which provides higher quality food more efficiently for the amount of space it uses, we can reduce pollution. And so, as we can see, we have 3 different tiers for each one of the things that we're doing on the planet. And the idea in these tiers is not saying that one of these is more technologically advanced than the other, or that they need to be upgraded in series of a farm version 1 to version 2 or version 3. It's rather to simply say tier 2 are things that have a more reflective albedo, and so they heat up the planet less, and or they produce less pollution for the same amount of production. So if we use strategies across the whole world that do that, we are moving to a world that's going to make less pollution and also reflect less light away from the planet, which will help us cool down, and that's what we're going for. Now, tier 3 is the same idea of much higher reflection of albedo and much more efficiency, but tier 3 might be things that we haven't yet developed. This is more basically, these are going to be very ambitious things, and so if we're making a model where we're being conservative, we would not include anything from this tier. If we're making a model where we're imagining that we're going to have magical technologies around the corner to help us out, then we can include things in this tier. Now that we've had a look at what the built tiles represent, we can see the average built albedo based on all of that information. And when we combine the built albedo with the wild albedo, we then get our adjusted albedo. And earlier on, when we were looking at radiation coming into the planet, we noticed that clouds do have a large effect on the amount of radiation reaching the surface of the planet. So here, we're not saying that this is the albedo of clouds, we're simply taking what our albedo should be at the land, and we're making it just a little bit more reflective by presuming that the clouds are helping us out. So now if we go back to our model here, we have math that's basically saying what our global pollution is now and what the annual pollution is being calculated at the bottom here. So if each year we increase pollution a little bit, then we'll see our total global pollution increases and our global temperature will increase here. So just to show you in a more dramatic way, we can increase temperature quite a lot based on how much carbon dioxide we are putting into the atmosphere. And then if we look at the albedo side of things, if we make the world more reflective, we can see the global average temperature going down, or the expected temperature to go down, and down, and down, and down. And if the world was a mirror, none of the shortwave radiation hitting it would be converted into infrared radiation, which means that regardless of the amount of greenhouse gases we had, they wouldn't be able to trap heat because they only trap infrared light, not shortwave radiation. So now we can see that albedo has a huge role to play in the expected temperature of our planet, and the greenhouse gas has a huge role to play in the expected temperature of our planet. And if we left our model alone like that, then unfortunately we would expect our world to already be at 16 and 16.35 degrees right now. So why is it that our target temperature is not the same as our actual temperature? And for this, we're going to look at specific heat capacity. Now, specific heat capacity is the amount of energy it takes to heat up a substance. Now, for water, it takes 4,184 joules to heat 1 kilogram of water 1 degree Celsius. For rock, it takes between 600 and 900 joules per kilogram, so obviously much less energy than water. For dry sand, it's around 800. For wet sand, it's around 1600, so we can see adding water to it increases the heat capacity a lot. And for air, it's around 1.2 kilojoules per meter cubed per degree Celsius. We can also see what it would be for a kilogram of air, but we are going to use the volume of a meter cubed because it'll be simple to work with in our chart. We do need to acknowledge that this is measured in kilojoules though, as opposed to joules. So this would be about 4.184 kilojoules instead of 4,184 joules. And then we also need to see how much of this stuff are we looking at. So for the average depth of the ocean, it's around 3.5 kilometers. And for the troposphere, which is the atmosphere above us, and the troposphere is the portion of the atmosphere closer to the Earth, which is around 12 kilometers high, and you can see most of the weather happens here and almost all of the clouds are here. This is also where most of the heat is generated by transfer from the Earth's surface. So for climate change, this is the portion of the atmosphere we're looking at. Now back on our chart, we can put in for air 1.2 kilojoules per meter cubed per degree Celsius. We're not going to include the entire troposphere, just the first 11 kilometers. We're not sure on what most climate models use. The measure for global average temperature just says the air near the surface, and the troposphere is the portion near the surface, but they might be talking about only 1 kilometer or even only 500 meters. So this is an estimate, and we're going to put in 11 kilometers just for the sake of it. And we see that the specific heat capacity for the volume of air we're heating is 13,200 kilojoules to heat it 1 degree Celsius. Now for water, we're imagining that the average square meter on our planet does have some land in it, so we're going to lower the specific heat capacity just a little bit, but the majority of what we're heating in the planet is water, and all of the climate models and climate scientists are agreeing that that's where most of the heat is going. And we made a mistake when we put down the number for water because I wrote it down in kilojoules instead of joules. And I didn't notice that mistake and then spent about 4.5 hours running through the climate model with different parameters and then noticed the mistake. So we're going to see what happens when we fix this mistake and why it doesn't really matter for how we ran the climate models. The only thing that's changing is our idea of the volume of the water that we're heating. And the reason this doesn't matter for our climate model is because we are scaling this volume to the observations of how the Earth is actually changing in temperature. So to go through this in a little bit more detail, we are looking at 1,000 kilograms of water for every cubic meter of water. We're looking at 4,000 joules per kilogram per degree Celsius. And we're going to say we're just measuring the top 2.5 meters of the ocean surface as what we're heating. That would give us this number in kilojoules to heat that volume of water 1 degree Celsius. And if we combine them, we then get this number. And if we rolled with that, we get our heating per year. And we can see that in 1981, we have been heating the world by 0.18 degrees Celsius per decade, which would mean 0.018 per year. So we can see that we want our calculation to give us roughly 0.2 of a degree increase per year. So how do we get there with all of this? Well, we start by saying, what is the temperature today, which we can observe? And then we can say, well, how is this going to change? Well, it's going to change based on the amount of extra heat we get each year, and we're trending towards our target temperature where we would be at equilibrium. But how quickly do we get there? So we say, what would the equilibrium of energy trapped be for the temperature we're at today? And that is this number here. Then we can see the difference between what equilibrium would be and how much energy we're receiving is here. And that is the forcing. Right now that's positive, so it's going to heat us up. Now, this forcing is in kilojoules per meter squared per hour, So if we say, what is the specific heat capacity of what we're heating up, which we calculated below here, and we say, what's the difference between the temperature we're at and the temperature we're expecting to get, which is here, so we're going to expect to increase 1.5 degrees, then what is the total amount of energy, or the specific heat capacity required to heat this amount of stuff by 1.5 degrees? So this means this number gets bigger by this amount. And then we say, well, what amount of extra energy are we getting each year? Well, that's our forcing. But this is in kilojoules per meter squared per hour, and we're looking at forcing over a year. So we take that number and we multiply it by 365, and then we see that since the sun does rise and fall over our imaginary square meter, the peak hours are the equivalent of around 8 hours per day of full sun. So we're saying 8 hours of our hourly rate times 365 days per year, multiplied by the amount of extra heat we're giving, and that is our forcing in kilojoules. We then take the amount of energy we need to hit our target heat, divide that by the amount of energy we're actually receiving per year, and that tells us it's going to take about 57 years to adjust the planet, or not the planet, the portion of the planet we're looking at, to the target temperature. That gives us about 0.17 degrees increase per year. If we fix the mistake that I made, and we convert that to kilojoules instead of joules, we see that suddenly the forcing is really dramatic, and it doesn't work anymore. We would expect to reach 26 degrees Celsius even though the equilibrium is at 16 degrees Celsius. And that just doesn't make any sense. And that's why, even though we did make a mistake, we're not going to change the models and rerun them again. All we're going to do is fix our scale by saying, instead of looking at 2.5 meters of water that we're heating, we're going to say 2.5 kilometers of water that we're heating. And when we do that, we get the same total specific heat capacity as we had before, and so the math that we get out of it doesn't change, and we're not going to change all of the models and rerun them for another 4.5 hours. All we're going to do is acknowledge that instead of thinking that we're only heating the top 2.5 meters of water per year, we'll think that we're heating the top 2.5 kilometers of water, which is possible because the ocean does have circulation, there is mixing going on. And that means that for the long-term heating, instead of 80,000 years for us to adjust, it would be more like 80 years for us to adjust. By fixing the mistake, we get a better understanding of the amount of the volume of water that we're heating every year and how long it will take for us to eventually stabilize the temperature. But our expected temperature at the end of each year is going to be the same as it was before, because we're scaling our model to fit the observations that we have today. Now, this part of our model also relates to the El Nino Southern Oscillation, which is about El Nino, La Nina, and neutral states. And basically, La Nina is when the Pacific Ocean is colder than the average temperature of the world's oceans. El Nino is when the Pacific Ocean is warmer than the average temperature of the world's oceans. And understanding why this happens and why it changes is a little bit complicated, but in a nutshell, we're looking at the amount of circulation of the oceans in that area. And in El Nino conditions, there is less circulation, so there is warmer water at the surface, and in normal conditions, there is more circulation. In La Nina conditions, there is accelerated circulation, and so the oceans get even cooler than you would expect. So if we go back to our chart, we could see that if this is what we expect the increase in temperature to be for the year, and we say that the circulation of the ocean is increasing, then we're going to say that we're mixing the water faster or exposing a greater volume of the ocean to heating each year. And if we do that, we can see that our expected temperature at the end of the year is actually lower because we now have more stuff to heat up. And if we slow down the circulation of the oceans, then we can see that the temperature gets warmer. Now, we're not going to include ENSO in our model because it fluctuates to make things both warmer and colder, and over time that ought to average out. In reality, this does affect the climate and should be in climate change models. However, we are not going to include it in our model today. We just want to acknowledge it. And with all of that together, we now have a model that only includes changes in albedo as a feedback, and it does fit the IPCC expected climate change models for how we would get temperature and the rate of change of heating per year. And if we run a model, we can now imagine what would happen if we did a business as usual case. So this is our business as usual model using no extreme feedback loops. So the only feedback we're looking at is the global albedo changing. You'll also see that we're not including all of the changes to specific cities, farms, and factories, etc. We're simply increasing our global annual pollution gradually over the years as we see that it is continuing to increase right now. What happens if we do continue to increase pollution? Well, we can see that our actual temperature every year will continue to increase, and we can see that the target temperature of what equilibrium will be is also continuing to increase. So by the time we get to the end of our model, we'll see that our actual temperature will have increased by a full degree within about 40 years. Meanwhile, our target temperature will have increased by about 2 degrees over the same time period. So we can see that not only are things getting worse, but they're going to get much, much worse as we continue to go on. And if humanity is not expected to survive much, or at least civilization is expected to collapse by the time we hit 3 degrees, we can see that before the century is up, even in this conservative model, humanity will not be having a good time within this century based on this model. And it should be a little bit worrying that this model does look so much like the IPCC reports. I mean, after all, it was based on them, but one thing in common is that the IPCC reports do not model properly the feedback loops, such as what happens if all of the permafrost melts, or if all the methane hydrate is released, or if a lot more carbon dioxide is released from peat bogs around the world. These aren't the only feedback loops. You could imagine what happens if the oceans become unlivable for algae to grow. What happens if our crops fail completely? There's many more potential feedbacks along the way. But our report's not looking at all of those, which means it's quite conservative. And we can see that even though it's quite conservative, it's still abundantly clear that simply the portion of our increased greenhouse gas effect alone is enough to make our world unlivable within the next 100 years. Now, in this run through, we're calling it a best case scenario, but also not including extreme feedback loops except for albedo changes. This time around, we are changing all of the infrastructure on the planet, and this is a representation of how much we actually have to change the world in order to succeed. And you can see we're changing things very dramatically, very quickly, because we need to get not only to net zero, but past net zero. And so in this model, I'm imagining that perhaps within just 3 years, if we were able to transform almost everything on the world, not everything, but the majority of high-intensity industries and infrastructure, such as anything that's built around a car, we need to transform all of that stuff. And if we can do that in about 2.5, 3 years, then we get to net zero pretty quickly. But as we'll see, the actual temperature we're experiencing each year is still continuing to increase even after we hit net zero. In fact, even once we are removing as much pollution from the atmosphere as we are currently putting pollution into the atmosphere, the temperature of the world still continues to increase, because the equilibrium point, or in other words, the long-term heating of the world, is much higher than the temperature is today. So we need to take the long-term heating from about 16.5 degrees down to 14.9 degrees if we want to stop the heating. And so even though we are starting to remove pollution every year, it's still going to take a while until we remove the enough pollution from what's already in the atmosphere to bring our temperature down. And we can see that it was in this run through, it was about 10 years after we passed net zero and were actively healing the planet before our actual temperature finally began to go down. Even when it did begin to go down, it only went down by 1/1000th of a degree per year. Fortunately, as we continued to heal the world and remove carbon from the atmosphere, the rate of the cooling does also increase. But we'll see by the end of the model that even in 40 years, we still won't be as cool as we are right now. So no matter what we're doing, right now is the coldest the world will be for the next 40 or 50 years of everyone's life, even if we do everything we can to change. And that's something we need to acknowledge. Now, we've acknowledged that the climate models we've been running so far are ignoring a lot of feedback loops. So let's look a little bit more at what these feedback loops are. So here's a list of negative and positive feedback loops. Positive feedback loops increase the effect of global warming. Negative feedback loops decrease the effect of global warming. And we'll see as we go through these that they are each complicated in their own right, and many scientists today are still not certain about the exact amount of effect they will provide, and we'll understand this as we go through here. So increased clouds reflects more incoming solar radiation. However, there are some studies, which we'll look at in a moment, which say that if we increase CO2 to a certain concentration, that can break up the cloud cover. So whilst we might expect more clouds from increased water vapor, at a certain point we might expect there to actually be less clouds as temperature increases, or specifically as CO2 increases, which will also be an increase in temperature that comes along with it. Then we have potential for more rainfall from moisture. This can, however, change ocean circulation patterns, which can create an imbalance in where rainfall occurs. In other words, even though there may be more rain in the future, it might result in more flooding in some places and droughts in other places. Then net primary productivity increase. This means that if there's more carbon dioxide in the air, it might be the case that plants can then grow more and they have more ability to photosynthesize. However, this is also not very straightforward, because as temperature rises, this can actually negatively influence plant growth. So there may be more carbon dioxide for the plant to use, but there may be less water available, and it needs both of those things to photosynthesize. Then blackbody radiation is simply the idea that the hotter the Earth is, the more energy it emits. There's also chemical weathering, which is just one of the ways that we can capture carbon dioxide. And there's the ocean solubility pump, which is simply to say that the more water we have in the oceans, the more carbon dioxide it'll be able to absorb. However, there is definitely a limit to that process. Then there's the lapse rate and altitude temperature, which might have an effect on the way the greenhouse gas effect works as well, potentially weakening it. Now, then there's positive feedback loops, which increase the rate of climate change. And as they're summarizing here, the bad far outweighs the good for climate change scenarios. In other words, the potential for positive feedbacks is much greater than the potential for negative feedbacks, and that's why so many climate scientists are very concerned about these positive feedback loops. One of the biggest potential positive feedback loops is permafrost melt and also methane hydrate stored in ice in shallow oceans. And currently there's about 5 gigatons of methane in the atmosphere, but there are hundreds of gigatons of methane stored in permafrost and in methane hydrate in the ocean beds. Then the removal of ice high albedo, which is to say, as we already recognize, that ice reflects a lot more light than ocean, so we can see a difference of 84% radiation being reflected to only 5% reflected. Then there's the ocean circulation pattern disruption. This relates to when we were talking about how quickly do we reach the long-term heating versus short-term heating. The more the oceans mix, the more the energy that we're receiving is being spread out across the entire oceans, and therefore the temperature will go up slower. If the ocean stops mixing and we only heat the very surface, then the atmosphere around us and at the surface will increase much faster in temperature. Then there's sea level rise, which will not only cause damage to cities and cause salination of coastal farming areas and reduce our ability to grow food, but it also means that in areas like Antarctica, where some of the ice is not in the ocean and not floating on water, as the ocean level rises, more of the ice will be exposed to water, which will increase the rate at which it melts. Basically, they're talking about how further chunks of ice would outpour into the oceans here. Then there's rainforest, drought, and loss. And so even if we have more rainfall, if the rainfall doesn't fall where the forests are, the forests can still dry out. Then there's wetland methane release, which is similar to the permafrost release, except we're talking about stuff that's not frozen currently. Then as the forests dry up and there's less moisture in the soil, there's higher risk of wildfires. And because of this, we are starting to see that forests are turning from carbon sinks to carbon sources. And the last one they're listing is gas hydrates in shallow water, which is the methane crystals I was talking about previously in regards to the permafrost. And if we look at the NASA website, they have a slightly different list for feedbacks. And one of the things not included before is water vapor, which is the most abundant greenhouse gas. And basically, as the atmosphere warms, there will be more water vapor in the atmosphere. So we can see that there are many different feedback loops that we could be including in our climate model. And then just to briefly acknowledge that there are many, many more potential feedback loops than just the ones we've looked at. For example, even something as simple as phytoplankton in the ocean. This will be affected by climate change, and it will also affect climate change. So even some of the smallest life forms on our planet can play a role in affecting climate change. And if we look at phytoplankton, we can see that a while ago people believed that as the temperature increases, the amount of phytoplankton will increase, and this will help to reduce the temperature. So it is a negative feedback loop. However, one of the authors on that original paper later changed their mind and put forth a hypothesis that says the opposite is true. So in this paper we're looking at right now, we see the two different models created by scientists who were both working with some of the same data. And the oversimplification is that ocean warms enhanced phytoplankton growth versus ocean warms decreased phytoplankton growth. So obviously the simplified model doesn't actually explain anything here, and you have to read a little bit more of the science to understand what was going on. And it turns out that once we look at the complex interrelationships between nutrients, temperature stratification, the relationships between different cyanobacteria and phytoplankton, how they interrelate with one another, it turns out that the original idea is true, but only under certain parameters. And the anti-claw hypothesis, as it's called, is true if we look at how the world's actually working. So unfortunately, the result of this is that we're expecting that as the planet increases in temperature, we will get a decrease in overall phytoplankton growth, which means less oxygen and also less cloud formation. So overall, that'll result in an increase in temperature, which will then mean less phytoplankton, which will then mean an increase in temperature yet again. And so this feedback loop is obviously very important, and yet it's not included in the lists we saw before. Neither are many other feedback loops, and the reason is because the biggest impact of all of the feedback loops is likely to be the methane and carbon dioxide from permafrost, peat bogs, and methane hydrate in the ocean. So for our model, we're going to build a feedback loop that looks at including this in the model and see how this changes things when we run a business as usual or a best case scenario. And now we'll take some data being reviewed by Paul Beckwith to get some numbers to put into our model.
More about which of the reservoirs was releasing the massive amount of carbon. But I suspect, very, very warm temperatures, the soil dries out, the peat dries out, you get more carbon release, the permafrost thaws, you get biological activity, more carbon comes out, methane and CO2 and methane hydrates, the ocean's warming, the methane hydrates in the sediments on the continental shelves suddenly releases, you get bursts of that, and you get a much, much warmer world, and then it takes a long period of time for the carbon to be drawn back out into the rock reservoirs, etc.
So now we want to make a climate model that has an exaggerated feedback loop to look at in contrast to the conservative model we made earlier. So we're going to take data from the paper we just looked at and make a feedback loop based on that. Now, this is not going to be very accurate because a lot of things are not explained well in the image on the paper we looked at. What we do see, though, is that there are 600 gigatons of carbon in the atmosphere and 8,000 gigatons of carbon stored in a combination of permafrost, peat bogs, and methane hydrates. Now, if we see that today we have a CO2 equivalent of 507 parts per million in the atmosphere, we're then going to say that that must be around 600 gigatons of carbon. Therefore, the 8,000 gigatons of carbon of potential in the feedbacks we will turn into 6,760 parts per million of carbon equivalent that could be added to the atmosphere. We then have to say at what rate will this be released to the atmosphere. Right now, we're going to say that none of this is being released, which is not accurate because we know that some of these things are beginning to be released. However, they are not being released on a mass scale. The vast majority of it is still in the ground. So at what point would we say that all of it comes out of the ground? Well, the temperature maximum on the albedo chart we have here is 18.5 degrees, at which point we are not truly at an ice-free world. There is still ice around the South Pole at this point, but there won't be much ice anywhere else in the world. So if we took that as our hypothetical temperature for when all of this stuff would be melted and released from the ground, we would expect to get a 6,760 part per million CO2 equivalent increase by the time we reach 18.5 degrees Celsius global average temperature. Now, going back into the math for our climate model, we can add feedback over here by saying for every degree over 15 degrees, we're going to multiply that amount by the feedback we would get at 1 degree of increase. So in other words, this amount of CO2 equivalent multiplied by the number of degrees is going to give us extra greenhouse gas potential for the year. And as we might imagine, this could exacerbate our problem quite dramatically. Now, before finishing off our model, we're going to take a brief look at this paper about solar geoengineering and how it may not prevent strong warming from the direct effects of CO2. So what they're talking about is solar geoengineering is our attempt to artificially reduce the amount of sunlight that the Earth absorbs. And unfortunately, they have found that even if we were to do this and we still increase greenhouse gases anyway, the temperature might not go up at first, but once a certain concentration of carbon dioxide has been reached, it leads to breaking up cloud cover, and the loss of albedo from that gives us a dramatic extra increase in heating. More specifically, they found that once CO2 reaches over 1,200 parts per million, it can begin to break up the clouds, leading to an 8 degree Kelvin, or roughly 8 degrees Celsius, of extra heating on top of whatever heating we would expect from the CO2 concentration in terms of greenhouse gas effect alone. This is obviously a huge issue, but two things to consider are that this won't happen until CO2 concentrations get much, much higher than they are right now, so this is not something that we are worried about happening next year. But when it does happen, it will have a huge effect, so we're going to include it in our model. Now, to put that into our model, we're going to say that once CO2 concentrations alone reach over 1,200 parts per million, we're going to remove the cloud effect from our albedo. To calculate that, we're going to say a portion of the CO2 equivalent each year is carbon dioxide, and we're going to presume it's roughly 90% of our CO2 equivalent. That's not perfectly accurate. We're just putting it in here to get an estimate. And then we're going to look at the portion from our feedback loops with peat bog, permafrost, and methane hydrate. What amount of that would be carbon dioxide alone? We don't have a perfect answer for that, but we're going to presume that the methane hydrate will all be methane. We're going to, for the sake of this model, presume that the permafrost will come out as methane as well, and that the peat bog will come out as carbon dioxide. If we use the same principles from before to calculate our CO2 equivalent based on the gigatons of carbon in those sources, we would then get roughly 1,267 parts per million of CO2 coming out of the peat bog, and we would presume that all of that would be released once we reach around 18.5 degrees Celsius, which is also an exaggeration and not quite realistic. If we put that into that model, we then just watch this number, and when it rises high enough, we turn this number into 0 and see the effect. Now let's run this model, which has an over-exaggerated feedback cycle in it, and see what happens if we do a business-as-usual case. So once again, we're not adjusting all of the specific cities and factories and everything like that. We're just gradually increasing annual pollution and seeing where the temperature goes. And one of the things we'll notice is that the CO2 equivalent is beginning to rise a little bit faster because the feedbacks are kicking in now that we've crossed the 15-degree mark. And so our target temperature is already over 21 degrees just in about 6 or 7 years. Meanwhile, the actual temperature we're looking at hasn't even gone up a half a degree, and so it will be hard for us to tell if what we're actually experiencing in reality fits more of a reasonable or an unreasonable model, because it still takes a while for the temperature changes to actually catch up with us in the short term. However, in about 10 years from now, in this example, we've already crossed the 16.5 degree mark, at which point a lot of climate scientists expect that human civilization would begin to fall apart. And from there, we can see that the temperature then gets dramatically out of hand and the rate of increase increases, and our long-term equilibrium target reaches over 100 degrees Celsius in less than 15 years. Based on this, we can see why some people are so worried about feedback loops, because if they are this bad, then the world becomes completely unlivable in a very short time. Now, in that same model with unreasonable feedback loops, we're going to look at a best-case scenario for humanity. What happens if we change everything as quickly as we could? Now, the first time we ran our best-case scenario, we only used technologies that we have available today and we know work. In this version, we'll soon see that it's not good enough if the feedbacks are as scary as some people think they might be. So we can see already we're having a rapid decline in the global annual pollution being produced. However, we can also see that the global temperature is still continuing to increase. And one of the biggest effects of what we're able to do in this scenario is modify the albedos. So we can see that the planet's becoming a lot more reflective because of the human input, even though the ice is still melting and the global albedo is continuing to go down. The net result is that the planet's becoming more reflective because of the efforts that we're putting in to try to save it. Now, at this point, we can see that we've already run out of everything we can do with today's technology, and we're starting to rely on technologies that hopefully we develop in the next few years to help us out. This enables us to further increase the albedo of the planet to make it more reflective. Meanwhile, we see, though, that the actual temperature is still continuing to increase every year, and our global average target is also still continuing to increase each year, even though we are now removing more pollution every year than we're currently putting into the world, and we've changed the albedo of the planet so that it's much more reflective than it used to be. And this just shows you the scale of the power of the greenhouse gas effect if some of these feedback loops get out of hand. However, as we're acknowledging, we're presuming that these feedbacks as modeled here are still unreasonably high, and that's why most climate scientists do not believe that even if we change everything that we do on the planet and become carbon negative, that we still have no hope of succeeding. And this is an example of what we mean by tipping points when talking in climate science, because if we cross a temperature threshold where we now unleash all of these extra feedback loops, no matter what we do within our power, no matter how much we're transforming the albedo of the Earth or absorbing carbon dioxide even perhaps 3 times faster than we're putting it up into the atmosphere today, once those tipping points have crossed, there is really nothing we can do and we're doomed. And we see that in about 15 years, even in a best case scenario, we would still breach the 3-degree limit, at which point we expect civilization to fall apart. And it's because of models that are run not exactly how we've created them now, but that are focusing on the extreme potentials of all of the feedback loops, is why some scientists have lost hope already. And for that reason, we're going to run one more model, and we're going to try to make things a little bit more realistic, whilst at the same time acknowledging, and we hope you can all see from what we've been through so far, that no climate model is going to be absolutely realistic. There are just too many different parameters to include, and the amount of data required is too vast for us to accurately model it and predict what's going to happen. To make a more realistic model, we're going to adjust the effect of those extreme feedbacks, and we're going to do it by looking at this simple fact here, which shows that for every part per million of CO2 in the atmosphere represents 2.13 gigatons of carbon. So if we go back to our model, we can then see that that gives us about 704 parts per million for the peat and the permafrost, and 2,350 parts per million from the methane. We'll also notice that at 18.5 degrees, the world still had ice at the South Pole, so therefore we don't have an ice-free world, and we don't expect all of the methane hydrate to be released right away at 18.5 degrees. So we're going to shift the scale to 20 degrees, and we're going to shift the amount of CO2 equivalent to 3,755 instead of 6,760. This will make the effect of our feedback much less dramatic. However, we can still see that 3,750 parts per million is much higher. It's almost 10 times higher than the amount we have today. And if we did release all of that, we still would be not able to survive on the planet. So this is still a very scary feedback. It's just not quite the same scale. It's about half of the intensity as the way we ran the model before. This is still not realistic because the permafrost and methane we were imagining is going to release methane, not carbon dioxide, and methane is much more powerful of a greenhouse gas than carbon dioxide is. So if we take a conservative estimate, which is over the 100-year period, methane is 25 times more powerful than carbon dioxide, then instead of a total of 3,750 parts per million of CO2 equivalent in the atmosphere, we would be looking at around 77,000 parts per million in the atmosphere. And if we look at the 20-year time scale, where methane is actually around 86 times more powerful than carbon dioxide, then we would be looking at around 260,000 parts per million of CO2 equivalent if everything released. So in other words, our model, while we're making it more realistic by saying it'll take longer for the stuff to be released, and we have a better idea for the CO2 portion of what how many parts per million we'll get out of it, we're not using a real effect of methane in our model. So this is still a slightly conservative model, but in other ways may still be a slightly exaggerated model. That's why we're saying this is probably a somewhere closer to more realistic model, at least, than our very conservative or our very extreme model. So now we're going to look at our more realistic model and a best case scenario for humanity within that model. We'll notice that we're going to change everything on the planet as quickly as we can, using the best of what we have available at the moment to try to get us to net zero quickly. But even in a best case scenario, it's going to take at least a couple of years to do that, and probably a few more years than that. And the challenge is that while we're doing that, the global average temperature is still continuing to increase, and the global target temperature is also still continuing to increase. However, if we transform the effect humanity has on the planet, especially in terms of albedo, then we're able to counteract some of the effects of the greenhouse gases that are increasing. And we can see that once we finally hit net zero, our temperature still continues to increase anyway. However, our long-term global target temperature is decreasing, mostly because of the dramatic changes in albedo. But we can also see that as soon as we cross the 15-degree threshold or tipping point, we're beginning to get feedback from the methane hydrate, permafrost, and peat bogs. And we can see that the rate of the increase from the feedbacks is higher than the annual reduction to greenhouse gases that we're able to make. This means that the only way for us to be able to cool the planet is by altering the albedo at a faster rate to compensate for this. What ends up happening is a bit of a dance where we are increasing and decreasing our global long-term temperature, whilst the global average temperature still continues to increase. And the big question is whether or not we can get back down below 15 degrees Celsius so that we stop releasing all of these feedbacks so that we're able to survive. And what becomes obvious is that the further we get past 15 degrees, so if we went to say 15.5 degrees, then the amount of feedback we expect to receive would be much, much more significant, and it's quite likely that we would not have the capacity to be able to act anymore. And at that point, we would be reaching a tipping point which would represent the collapse of humanity and probably the majority of our biosphere as well. However, once we have got to the point where we're removing as much carbon dioxide as we reasonably can from the atmosphere each year, and we're able to increase the albedo as much as we can to our best capacity, we're going to imagine that we've now hit our limits for change. And the question is that good enough? And you can see that in this run of the model, we were able to just hit that balance point where the amount of impact we were having on the greenhouse gases was significant enough to bring us into a cooling effect. And when we went from a heating to a cooling effect, we were only cooling by about 1/1000th of a degree Celsius. And then the rate of cooling gradually began to increase, but it wasn't even 100th of a degree Celsius for another 10 years later on. So this shows that once we begin to heal the planet, it will still take a very long time for us to reduce the temperature back down to a healthier temperature for life on Earth. Now, in this model, we were successful, but it was only because we not only transformed the world as quickly as we possibly could by using all of the knowledge we had available to us at the moment, but we also continued to research and come up with new and innovative ideas to give us an even higher capacity to act. We also then put all of our resources towards acting and transformed what humanity's impact looks like on the world globally. Once we had done all of that and had altered the planet's albedo quite dramatically, and we were also cleaning up the atmosphere and removing carbon dioxide more than twice as quickly as we used to put it into the atmosphere. With all of that done, we were still only just barely able to survive by the skin of our teeth, and if we had waited even 1 or 2 more years, the feedback effects might have gotten too far out of hand for us to recover from. So to begin to sum up, we made 3 different climate change models. One of them ignores a lot of feedback loops and therefore is inaccurate in a conservative way. One of them exaggerates some feedback loops and is therefore inaccurate in an extreme way. And then the third one we know is not perfectly accurate, but it fits somewhere between the two. We then ran the conservative model with both a business as usual and a best case scenario, and the best case scenario allowed humanity to survive, whilst business as usual did not. Then we ran the extreme climate model, and neither the business as usual nor a best case scenario were able to allow humanity to survive. We then ran a model which is certainly not accurate, but fits somewhere between the two of conservative and extreme, and in that model we saw that a best case scenario for humanity does give us a chance of survival. However, the time frame for action is very short, and our chances of success are not guaranteed. The longer it takes for us to change, the vastly more difficult it will become for us to be able to change, and we will also be living with the consequences of a heated world for decades after we already begin to heal up the world. Now we need to acknowledge the elephant in the room, which is carbon sequestration. According to the IPCC, carbon sequestration is going to be required in a huge way if we're going to be able to achieve the targets for greenhouse gas levels in the future that will allow us to survive. In the model that we ran today, we had to cover more than half of the land surface area of the planet in carbon sequestration for us to be able to survive. Carbon sequestration is basically the idea of pulling carbon dioxide out of the atmosphere and storing it somehow. There are many different ways to do it, from simply planting trees and letting them grow, to building complicated machinery that uses chemicals to draw carbon dioxide out of the air. Now, there is a lot of controversy around carbon sequestration, and since it plays such an important role in whether or not humanity will survive in the future, it's worthwhile looking at it in a little bit more detail. Now, on the one hand, if we look at the idea of planting trees, we can see that different biospheres create different amounts of biomass. For example, in deserts, they generally make between 0 and 120 grams per meter square per year, as opposed to tropical rainforests, which produce between 2 and 3 kilograms per meter squared per year. And since about half of the biomass of a tree is carbon, this means that if we create more tropical rainforests on the planet instead of deserts, we will be able to capture a significant amount of carbon. And if we take some of the figures from biomass and we look at the amount of forest cover that's changed in the last 100,000 years, if we imagined reforesting the world to how it used to look, we could potentially capture around 15,000 gigatons of carbon. That is almost double the amount of carbon that we are terrified of releasing in permafrost, methane, and peat bogs. Therefore, reforesting and healing the world definitely has the capacity to make the kind of impact that we're talking about. So when looking at our model and seeing that we may have to cover about half of the planet's surface in carbon sequestration, we could imagine instead of building machines and technology to do that, we could simply be reforesting and healing at least half of the planet. And I would like to believe that that is a source of hope for humanity. On the other hand, in terms of the technological side of carbon sequestration, I just don't have as much faith there, and here's a brief clip to give you an idea of why I might feel that way.
If you add all that up, which the authors of this paper kindly did for us, then the news is that all pathways limiting warming to 1.5 or 2 degrees will involve carbon dioxide removal during the 80 years between 2020 and 2100 that range from 450 billion tonnes to as much as 1,100 billion tonnes. So the next question might reasonably be, what's the plan? If we then overlay the three scenarios from the last chart, it's pretty clear that things are going to go very pear-shaped in the coming decades unless there's a serious ramp-up in government action on carbon dioxide removal. To get a gauge of current thinking on the subject, the report's authors went through what I imagine was an extremely painstaking process to identify where the balance of research has been progressing over the years. Today, as our knowledge of the pros and cons of the various CDR techniques has improved significantly, the most researched area is actually biochar, representing the big purple section, followed closely by soil carbon sequestration in general, again shown in dark green. By contrast, the report found that of the roughly $4.1 billion of direct funding currently in place, the vast majority, about $3.5 billion, is being ploughed into proposed direct air capture demonstrators in America. Now, the authors of this paper are very careful not to cast any aspersions whatsoever on the various direct air capture companies currently operating around the world. So what I'm about to say is purely my point of view and does not represent the views of the paper's authors. But in my humble opinion, what's happening in the real world is that innovation in CDR is morphing into intellectual property that can be used by existing big businesses, many of which are based in or have close links with the fossil fuel industry, to create profitable new enterprises. Purchases of carbon credits for removed carbon dioxide reached about $200 million between 2020 and 2022, most of which came from DACs. Two of the biggest DACs companies operating today, Carbon Engineering and Global Thermostat, are either using their sequestered CO2 for enhanced oil recovery, which ekes out otherwise unavailable pockets of oil from depleted oil seams, which of course then gets burnt and releases all its carbon dioxide back into the atmosphere, or they're combining carbon dioxide with hydrogen to make hydrocarbons that they can sell as so-called net zero fuels. Meanwhile, the report highlights high-profile press releases from various companies and industry groups announcing their intentions to scale up CDR activity in a way that implies we could actually achieve the mid-century targets we looked at just now, not just with DACs, but also with biochar and BECCS. The trouble is, as the authors of this paper point out, in order to genuinely achieve those claims, the carbon dioxide removal industry would have to scale up by 5 orders of magnitude. That means getting 10 times bigger, then 10 times bigger again, then 10 times again, 10 times again, and 10 times again. I'll let you draw your own conclusion from that statistic. The conclusion that the research team draws from all this analysis is that the coming decade will be a crucial time for new CDR technologies. Essentially, say the authors, if we don't get a move on now and start hitting some serious targets in the next few years, then we really will have left ourselves with an impossible task during the second half of this century.
So none of this is meant to say exactly what will happen in the future, but hopefully now you have a better idea of why some climate scientists think we're going to be extinct in a couple of years, whilst others think we have much longer time to act. We can also see, unfortunately, that the IPCC report actually fits the more conservative model, and so in trying to imagine the future we face, it's not actually a necessarily realistic projection of what humanity is in for. Nevertheless, all of the climate models and everything that we have learned through exploring this shows us that we are able to succeed only if we achieve net zero as quickly as possible and then continue to go past that to actively heal up our planet. And part of our strategy ought to include changes to albedo, such as removing roads and parking lots from existence and replacing them with something that reflects more light or is a little bit healthier. We can also see that even the climate scientists who have studied this problem in great detail are not certain about exactly what will happen because there are so many different feedback loops and all of them are so complicated that to be able to accurately predict what will happen in the future, you would need an infinite data set and an infinitely powerful supercomputer. This means that we cannot wait for certainty from scientists to say what will happen. What we need to do is take the warning that they have been giving us and are continuing to give us, which is that in all of the models that we look at, the only path of survival for humanity is to transform the way we're acting on the planet to not only become climate neutral, but to become climate negative and to heal our world as quickly as possible. If we do our very, very best, there is a real chance that we can survive. If we do not do our absolute best, it appears that there is no chance that we will survive. Thank you for watching. Hopefully today you've learned more about how climate change models are made, why they're not perfect, and yet why they do give us a clear understanding of what humanity needs to do to be able to survive in the future. Please like, subscribe, and share. And if you, like me, are skeptical about the capacity of our current global socio-economic system to be able to allow humans to succeed in the challenge that is ahead of us, then please look at some of my other videos which discuss alternative ways for human beings to cooperate in taking care of the planet. Thank you, and I hope you all have a great day. And as sort of a postscript, for fun, let's go and look at what we got wrong in our model and how that likely changed the results. To start with, we used a map of the world that we turned into a grid. This is wrong because the world's an oblate spheroid. It is not a two-dimensional flat map. This means that the amount of area that we dedicated to the North Pole and the South Pole is far greater than in reality. Also, we put down the specific albedo for each area of the land. Because we considered 1 square to be a large area of the land, we are averaging that square, which means that our numbers are not going to be very accurate. Furthermore, from the data set that we looked at, we know that this should be around 6% reflection instead of 10% reflection for the deep ocean. So again, that makes us not quite accurate. Then we saw that when we calculate the total energy for the planet based on the angle of light hitting each of these surfaces, is a different result than if we look at the global average albedo and the global average angle of light coming in. And so we know that that makes our chart wrong. Then when looking at how albedo relates to the temperature of the globe, we only set the albedo for an end state and a beginning state, and then we made a smooth transition all the way through. How the world actually reacts is going to be more dynamic than the way we created it here, so once again, this is unrealistic. And we looked at what humanity is doing to impact the world. We did not include the actual number of cities, farms, factories, or any of these things. We used an approximation for them. We did not include the actual amount of pollution or the scale of it in an accurate way for each of these industries. We just scaled pollution to give us the total parts per million that the world was producing at the moment. And that makes things more unrealistic. We also presumed the albedo of each of these things, which was not very specific or realistic. We also looked at transforming things simply between tier 1, 2, and 3, when in reality there are probably 100 different ways to make a farm or a city or a factory. We also looked at the scale of albedo changing with tier 2 and tier 3 cities, and we're not sure that that's actually possible. So for example, you can't make a forest or a farm fully reflective, or they're not going to absorb the sunlight that the plants need to grow. Next, we looked at the difference between short-term and long-term heating, and we imagined that we need a certain volume of matter that we're heating up, and we decided to calibrate our model to the observations of how the world is changing. We found that the volume would be about 2.5 kilometers depth of ocean per square meter to get us the temperature changes that we are witnessing today. However, we're not at all certain if that math's accurate, and then our estimate for the total long-term heating again is not necessarily accurate either. Then when looking at feedbacks from permafrost, methane, and methane hydrate, we calculated it in terms of carbon dioxide only. We did not look at if it came out as methane, so that's not accurate. We also arbitrarily picked 20 degrees at the point at which all of the feedback would reach its full effect. However, even when the surface of the world is at 20 degrees, there may be parts of the ocean that are still cold enough to have methane hydrate in it, so we're not certain that all of it would actually be released at that point. We also made the rate of release linear, as in it goes up gradually as temperature increases. There's no evidence to be sure that that would happen either. We then try to find an estimate for the portion of carbon dioxide that would come out from all of this. This cannot be accurately estimated either, because if we look at Siberia right now, there are a lot of wildfires burning where there is also permafrost, which means there's potential for methane being released to actually be burnt right away and then converted into carbon dioxide and not be released as methane. And the problem is trying to predict how much of these feedbacks will come out of the ground on fire versus go directly into the atmosphere is pretty much impossible to predict. Then we looked at the effect of albedo in terms of cloud cover, which is also including aerosols, things like sulfur dioxide, and we came up with a number for that based on making our model fit the IPCC reports. This is not based on how much clouds there actually are in the world or how cloud cover is changing, so again, this is not accurate. Also, when calculating the total greenhouse gas equivalent, we made an arbitrary amount for water vapor. However, the amount of water vapor will change, and so this is not accurate. So as we can see, pretty much every single part of our climate model is not actually accurate and should not be used to predict what will happen in the future. Nevertheless, our conservative model does fit quite well with the IPCC reports, especially giving us a 3-degree global average increase by the end of the century, and our more exaggerated reports do fit with what some climate scientists are saying when they imagine that the world will be unlivable in just a few years. And that means that our more realistic model, despite not being accurate to the world, does fit somewhere between the IPCC conservative reports and the alarmist extremist reports, and is therefore probably in the realm of reality, even though we know for a fact it cannot be perfectly accurate.